So today we are going to see about the topic interaction of radiation with matter. Yeah. So interaction of radiation with matter. Like before going into the topic, first we have to know about the two terms, that is what is radiation and what is matter. The first one is radiation. Radiation is generally considered as it is an emission of energy as an electromagnetic wave or a moving subatomic particle. So we can say that an energy is released or energy is spent in the form of an electromagnetic wave or a we can say it is in the form of a subatomic particle. So hence we can say that radiation has a dual nature. It has a wave nature as well as a particle nature. So simply we can say that it is emission, electromagnetic wave and particle. Yeah. The second one is matter. So matter is a collection of so many particles, or simply we can say that a collection, a group of particles or a group of system is called as the matter. Here we can generally in a simple term we can define it is a substance that has inertia and a physical size. Something should have a physical size that we mention as the matter. At the same time, it consists of elementary particles as electrons, protons and neutrons, and they should have a definite mass and a size. So we call radiation as emission of electromagnetic wave and a particle or a moving subatomic particle, and it's very important that it should move. It's not a stationary, it should move. Second one is a matter, which is a collection of substance that has some inertia and a physical size, and these collection of particles all considered to be the elementary particles which has a definite mass and size. And actually the topic today we are going to deal is interaction of radiation with matter. When the emission of an energy passes through a matter, a group of substance, what kind of reactions takes place, that we are going to deal here. So before going into the topic, we should know about the concept called photoelectric effect. Yeah. The concept of photoelectric effect for first given by Heinrich Hertz. In the year 1887. So actually it was an accident. When he was doing some experiments with the resonance electrical circuits, he found out that when a beam of light falls on the electrical circuit, he found out electrons are getting attracted, like from the particles electrons are getting attracted by the positively charged particles. Like it's just the beginning. Later on, after a year, which means in the year 1888, Hallwachs and his associates in the year 1888, he proved experimentally. He did an experiment to show that when a beam of light falls on a particular object, it emits a particle. That is why by sending a wave, how we can emit a particle, that is what we are dealing with, the interaction of radiation with matter. So in order to deal or in order to understand briefly about this, now we have to move on the Hallwachs experiment. Yes. First we'll go with the experimental setup. The experimental setup is like this. The experimental setup consists of a battery which has a positive and negative terminal, and this pure, like the circular part, is called as the quartz bulb, which is evacuated, and in between we have two zinc plates. So they are zinc plates, and the plate which is connected to the negative terminal of the battery will act as a cathode. As we know, cathode is a negatively charged part, and anode which is connected to the positive. So anode is always positive. Cathode is for negative and anode is for positive. So now we have connected a galvanometer in series in this circuit. Actually, the function or the purpose of galvanometer here is, galvanometer is a device which is used to detect the presence of electric current in a circuit. When the experimental setup is fixed like this, now if you notice in the galvanometer, there will be no flow of current, which means there is no deflection. So the reason behind this is, we have a gap here. It is like evacuated one, there is a gap. So there is no flow of current. Here we can say that it is an open circuit, means the circuit is broken. Now he had sent, that Havoc sent electromagnetic radiation, such as we can say ultraviolet radiation. When he sent an ultraviolet radiation and made it to fall on the zinc plate which is connected to the negative, and it is called the cathode, he found out that some of the electrons are emitted. So the proof how he has found out is, when he sent the electromagnetic radiation to fall on the cathode ray, now he has saw some deflection in the galvanometer. So which means, when the electromagnetic radiation falls on the negatively charged particle, the cathode plate, electrons are emitted, and this is a positively charged plate. Hence, the electrons emitted gets attracted by the positively charged anode, the plate. Hence, it forms a closed circuit. Now, the current starts to flow. So this is the evidence, or this proves the existence of electrons when a radiation is allowed to fall on a metal surface. Now, so in order to prove, next he has done the same thing. He has connected the same circuit with a galvanometer, a quartz bulb with a battery, minus plus, cathode anode, and this is the galvanometer. Now, what he did is, now he changed the direction of the incident ray. Now he made the incident ray UV rays to fall on the anode, which is a positively charged. And here again, this plates will emit electrons. You can see that electrons are get emitted. At the same time, here this plate is connected to the negative terminal, and here the excess of electrons will be there. So electrons gets repelled. Hence, there will be no flow of current, which means the galvanometer does not shows any deflection. So this proves finally, when a beam of light made to fall on any metal surface, electrons are get emitted. So this was the first evidence, or this was the first experimental proof for the interaction of radiation with matter. Next one, in order to understand a deep concept about what is a light, what is a wave, what is a particle, we should know about the light wave first. So simply we know it is a light. So light is in the form of a wave. So this light is a form of a wave, and we call this as an electromagnetic wave. It's an electromagnetic wave, and this was proposed by Maxwell. Just he said that light is a form of an electromagnetic radiation, it is a wave. Light always travels in the form of a wave, and this was proposed by Maxwell, but he didn't say, or he does not give any evidences for whether it will travel as a particle. Later on, it was proved to be a particle by the scientist Max Planck. Max Planck, in his theory, and this theory we call as a quantum theory. The theory is a very important theory in the field of physics, quantum theory. So how this theory arises? So according to the concept of Max Planck, so when a light wave, so first they have said that it is in the form of a wave. So we call it a light wave, it's electromagnetic wave. When a light wave is traveling, it is just traveling, and it is traveling in the form of, simply we say that light is emitted in the form of a discrete packets of energy. We call as a discrete packets of energy called quanta or photon. So very important, this is quanta and photon. So light is emitted in the form of a discrete packets of energy called quanta or photon, and each photon, or simply we can say that each quanta is having the energy is directly proportional to the frequency of the radiation. So the frequency of the radiation is directly proportional to the energy of the radiation, or simply we can say that the energy of the radiation is directly proportional to the frequency of the radiation. So now this will be equal to a constant, and that constant was given by Planck, and hence we call that as a Planck's constant. So E is equal to h nu, where h stands for the Planck's constant, and experimentally it was proved that the value is 6.626 into 10 power minus 34. So this was the first existence or the first proof for light travels in the form of a particle and a wave, and this finally proves light has a dual nature. So light travels as a wave as well as a particle, which means Maxwell proved electromagnetic wave, light is in the form of a wave, and later on Max Planck proved that light travels in the form of a particle also. Hence light has a dual nature, particle as well as wave. So now if you want to study the different phenomena in physics, if you want to study the phenomena of interference, diffraction and polarization, so light behaves as a wave. So very important, if you want to study about the phenomena of interference, diffraction and polarization, light travels in the form of a wave. And if you want to study about the phenomena of absorption, emission and the interaction of materials or interaction of matter, of course our topic, the interaction of matter, here light travels in the form of a particle, and that particle is called as photon, here it's called quanta. So this was the first evidences for light has a dual nature. So now after Max Planck, the famous scientist of every time, Einstein. So we call Einstein's photoelectric effect. Einstein's photoelectric effect. So first, Heinrich Heinz given a small hint or its experience as a spark for the photoelectric effect. Later on, the associates of Halbwachs, they have proved experimentally how electrons are get emitted, and finally our Einstein, he gave an equation for the photoelectric effect. So according to the concept of Einstein, so as we know that when a ray of light or a beam of light falls on a metal surface, so it emits electrons. It emits electrons, which means a sufficient amount of energy is given to the material, and hence the electrons are taken out. So simply, before going to this topic, we should know about the atoms and its properties. We know that protons and neutrons constitute the nucleus, and electrons are in the outermost of the nucleus, and they are revolving in a particular orbit. And the electrons which are very much far away from the nucleus, they are loosely bound with the nucleus. As we know, here it represents a positive, and hence nucleus consists of a positive charge, and electrons are always a negatively charged particle. So the negatively charged particles are always get attracted by the positive, and then they make a particular orbit. But here the number of electrons are very more than the number of protons. So electrons which are very near to the protons, they follow a particular orbit, but the electrons which are very far away from the nucleus, they don't have any particular orbit. They can move here and there randomly, and they are called as a free electrons. The electrons which are free to move, they are called as free electrons, and to take out the free electrons from an atom, very sufficient amount of energy is required. But I am telling it's a very sufficient amount of energy. But even though the energy should overcome the energy which is supplied to overcome to take an electron out. A good example we can say that simply when you are rubbing our hands, it produces heat. Actually what happens behind this, when I am rubbing my both the hands, electrons and electrons are interacting, which means atoms and atoms are interacting, and hence the exchange of electrons takes place, then it produces heat. Even when I am doing like this, I cannot, and when I am rubbing like this, which means here the frictional force giving an external force to that, and hence it takes out the electron. This is the concept behind this. So the energy which is given to this plate is sufficient to take out electron out. So he calculated the energy given into two, half and half, or simply you can say that two parts. The energy has divided into two parts. First one, the energy which is given should do some work to take an electron out. The energy which is given to do some work on the plate or on the particular object, to do some work, and that is we call as a work function. Actually the definition of work function is it is a minimum energy to take an electron out from the atom. So the minimum energy required to take an electron from an atom, that is we call as a work function. The first one is a work function and second one is the kinetic energy. So now we have given the energy to the atom or the particle and we have taken out the electron. So we have done a work and that work function gives us the electron. Now when the electron comes out, where it will go? So they should move. So in order to move, the energy which is given gives a sufficient kinetic energy to the electrons to move further. So half of the energy which is transferred will be work function and remaining will be the kinetic energy, that is half mv square. So the energy here given E is equal to W plus kinetic energy. That is the total energy which is given as a radiation will be equal to the work function plus the kinetic energy. Now work function, the energy. So here in the place of energy E, I am going to replace with h nu. So according to Max Planck, h nu is equal to the work function is W plus half mv square. Considering this as equation number 1. In case when the electrons present inside the atom, so they collide with each other, because we know electrons are negatively charged. Same charge always repel. When they are repelling, they lose some of its energy. When an electron is sufficient, like it has some more energy, and when you are taking out, it has a maximum velocity to move, and hence we are replacing this equation as h nu is equal to W plus half mv max square. This is equation number 2. So the energy is equal to work function plus half of mv square, and here the velocity of the particle, which is the velocity of the electron which is moving, has a maximum in case if they doesn't have any loss of energy inside the interaction with molecules. And this equation is generally referred as the Einstein's photoelectric equation. So this is generally called as the Einstein's photoelectric equation. Now, if we are giving a frequency, a particular frequency, and that frequency is called as a threshold frequency. So actually the meaning of threshold frequency is the minimum frequency or the least frequency below which the emissions of electron is impossible. Means if you are reducing the incident rate to fall on the metal surface, if it is very low, only a certain amount of energy can be out. After that it cannot be taken. So here it is represented by h nu naught. So nu naught represents the 0, which means minimum will be equal to the work function plus half the mass is a constant, but here the velocity will be equal to 0. So here h nu will be equal to w, since this equation becomes 0. So now considering this as equation number 3, substituting equation 3 in equation 2, we get, so in the place of w we are going to substitute h nu naught. So already h nu is there, that is equal to h nu naught plus half m v square max, and I am just taking h nu minus h nu naught, bringing this side, will be equal to half m v square max, or h is constant in both, so nu minus nu naught is equal to half mv square max. So this is the another modified form of Einstein's photoelectric equation. So generally this equation is considered as the Einstein's photoelectric equation, and this is called as the modified Einstein's photoelectric equation. Simply in a word we can say that if you are allowing a ray or a beam of light which is having a sufficient energy or frequency to incident on a metal surface, it emits an electrons. This process is called as a photoelectric effect. Means the emission of electrons from a metal surface by sending or by allowing a frequency of electromagnetic radiation, we call that as the photoelectric effect. And the electrons hence evolved, the electrons are just obtained or called as the photoelectrons. So this concept was first given by Hendrik Hertz, later on proved experimentally by Halbach, and it was theoretically verified by the equation by Einstein. So this is one concept. Next one. It's a matter waves. Matter waves. At beginning we have deal with radiation and matter, and we have find out that a matter is a substance which has some inertia and have a physical size, and it consists of electrons, protons and neutrons of definite mass and size. Okay, now as we have already proved that matter is also travels in the form of wave at the same time as a particle. Actually, first thing you have to know, matter is a particle, but it travels in the form of a wave. So this was first proposed by a French physicist. The famous one is Louis de Broglie. So when we are talking about electrons or talking about radiation photoelectric effect, Hendrik Hertz, Einstein, Halbach and de Broglie, they are the unavoidable names. We cannot leave these names. Without them, these topics are incomplete. So finally we have the Louis de Broglie, and he gave in the year 1924. He said that when a radiation can be twice a dual, which means a radiation can be as a wave as well as a particle, why can't the matter? So it's a substance, why can't it matter? And he strongly believed and he strongly proposed the theory of this, and he finally proved that a matter always, it's a particle, a matter particle always travels in the form of a wave in a certain conditions. Under certain conditions, it will travel in the form of a wave. And hence he proved that when radiation can have the dual nature, why not the matter? So this was the first existence of matter waves, and he also proved theoretically. He has given some derivations to prove the wavelength of a wave and the wavelength of an electron. So now we will go one by one. The first one is de Broglie's wavelength of matter waves. De Broglie's wavelength of matter waves. So for this, he has taken the particle as well as the wave, and he has taken the particle nature from Einstein and the wave nature from Planck. So he said that according to Einstein, E is equal to mc square. The energy of the incident radiation is equal to, for a particle, the energy of the incident radiation will be equal to the mass of the particle into the square of the speed of the light. The square of the speed of the light. And he has taken the wave nature from Planck, and its equation is E is equal to h nu. Equation 1 and 2. Now, from equation 1 and 2, it's both are equal, so we can write h nu is equal to mc square. Means this is equal to this energy of a particle and the energy of a wave, both are equal. Now, we know speed, simply we can say speed v is equal to distance of a wave lambda by time. Lambda by time, and this speed is here represented by c. So c is equal to, or else like we can keep nu. Oh, sorry, we are keeping as v only, lambda, and we can write 1 by t as nu. It is nu on, okay, and we are keeping as c. This is c is equal to nu, since 1 by t is equal to nu. So in the place of 1 by t it is nu. So nu is equal to c by lambda. Nu is equal to c by lambda. So now we are going to substitute here. So it will become h c by lambda is equal to mc square. Now we have to find out the wavelength. Actually, our aim is to find out the wavelength of matter wave. So lambda is a wavelength. So lambda is equal to hc by mc square, or lambda is equal to h by mc. Here c stands for speed of light. And here if you are considering for a particle, so we will consider c is equal to v, the velocity. Speed and velocity both are same. So lambda is equal to h by mv, or lambda is equal to h by p. So both are the common equations. So equation 3 and equation 4. So here, since momentum p is equal to mass into velocity, so mass into velocity is nothing but linear momentum, and this is the de Broglie's wavelength for the matter waves. If we know the value, h is Planck's constant, m is mass of particle, and v is velocity of the particle. If you know the value of, and h is already it's a constant we know, and if you know the mass of the particle and v of the particle, then we can easily find out the wavelength of matter waves. So this is the first evidence, or this is the first value or the equation which is given by de Broglie to find out the wavelength of matter waves. The last one is, so when you are doing for the wave, of course we have to do for the particle. The next one is de Broglie's wavelength of an electron. So electron is a particle, so we are going to find out the wavelength of an electron. So for this, let us consider a particle, for example an electron which has a mass m, charge E, and the potential is equal to V, and we know the energy supplied to the particle, and hence the particle moves and it possesses kinetic energy. So we are writing E is equal to half mv square. Here in the place of energy we are not using h nu. for the frequency of the wave. So here we are going to use EV, where EV stands for electron volt, because it is a particle. Nu frequency, if you are writing E is equal to h nu. So this is for the frequency and that is for the wave. And here we are going to deal with electron, it's a particle. So we are using E is equal to EV. So I am replacing EV is equal to half mv square. Now keeping v square here, just I am replacing 2 EV by m, or simply v is equal to the square root of 2 EV by m. So next, from de Broglie's wave equation, we have lambda is equal to h by mv. The wavelength is equal to h by mv, and if you want to substitute in the place of v this, or else consider this as equation number 1, this is equation number 2. Now substitute the value of v in equation 2. We get lambda is equal to h by m root over 2 EV by m. So now bringing this m inside, so lambda is equal to h by root over 2 EV m square by m cancels. So lambda is equal to h by root over 2 EVm. So this is the equation to find out the wavelength of a particle. For example, here we have taken as the electron. Now by substituting the values, here we know h is equal to 6.626 into 10 power minus 34. Next one is electron. The charge of electron is 1.6 into 10 power minus 19 joule. And next one is mass. So this is mass. So mass of an electron is 1.9 into 10 power minus 31 kg. If you are substituting these known values, these are constant values. If you know the constant values, we will get lambda is equal to 12.27 divided by root V angstrom. So here angstrom stands for the unit, which is equal to 10 power minus 10 meter. So lambda is equal to 12.27 by root V. Here I am just keeping root V because we don't know about the potential, the energy which is given. How much we don't know. For example, if V is equal to 100 volt, if you are substituting V is equal